In the last class, we have seen what is the physical structure of the NMOS transistor, right? Okay, so we concluded something like this. We have a body, right? We have N plus source, sorry, one plus N plus one region. There is another region called another N plus. Okay, on top of it, what we have done, we created one oxide. On top of it, there is a polysilicon. Okay, so this is called an oxide layer. And definitely we have another material that is called P plus. It is actually a body, right? Okay, please remember that this body is always connected to ground. What is the reason we need to connect it to ground? We are not allowing any body current. Okay, therefore it must be a reverse bias. Okay, therefore the current flowing through this one is actually IB. That value is equal to 0. That means it should not make any kind of junction current between the any P region. Okay, sorry, any N plus regions. Okay, since all these things actually P substrate. Okay, so this P substrate actually cannot be connected to cannot be provide any kind of current with the N plus regions. Okay, right. Okay, and we have seen that we applied some kind of potential at this terminal. Okay, definitely we call this as a body, right? Body or a bulb. Body or a bulb. Okay. Now we applied some potential at this place, right? Okay. Depending upon whatever the potential that we applied here, okay. Under the silicon dioxide, so under the silicon dioxide means this is the region. Under the silicon dioxide, we have seen immobile ions. We have seen immobile ions or the depletion of free carriers from there. Okay, depleting the carriers from there is called depletion mode. Okay, so therefore here we have depleted the carriers. That's the reason why we have equal and opposite ions will be available, right? Okay, therefore under the silicon dioxide we don't find any kind of immobile the free carriers, right? Holes cannot be there, since actually these atoms are associated with the three holes. Because of the positive potential at the top, all the free carriers are depleted towards the bottom side of the P region. Okay, therefore it has got immobile ions. If you increase further here, what will happen? Further depletion of the carriers are existed, right? Further carriers are existed. Okay, so therefore here also you can see. Therefore, we observe that this is an immobile charge. Again, this is also insulating material also has immobile charge. Altogether, we call it as a, this is the thickness of the oxide. Okay, initially the thickness of the oxide is this much only. Initially the thickness of the oxide is this much only. Tox. But now the Tox will be Tox dash something like this. It is increased. Okay, of course, definitely all the free immobile charges are just below the oxide only, because its size is very the huge size when compared to the free carriers. Okay, therefore definitely I can also write the immobile charges here also. Okay, let me, I don't want to write it this way, but also that are occupied entire region, silicon under the silicon dioxide. Fine. Now, if you further increases the positive charge on the top plate, okay, due to the less capacitance, the carriers cannot be depleted. Okay, so as we have mentioned that since it is simply it's a mass capacitor, right? Okay, therefore the capacitance is actually epsilon A divided by D that we can see, right? D is the distance between the two plates. If the distance between the two plates is more, definitely the capacitance will be less. If the capacitance is less, okay, so whatever the charge that you put, that is not able to induce the opposite charge on the other plate. The electric field is not able to attract the, deplete the more carriers. So therefore, but definitely, okay, the electric field has to produce, so that means equal and opposite charge carriers must be there between the two plates, right? That's the reason why these free carriers will available here, okay? So therefore, where these free carriers are coming from? These free carriers are coming from N plus region, okay? If you keep on increasing the if you keep on increasing the top plate charge, so more and more carriers are accumulate is available under the silicon dioxide. What carriers these what are these carriers? Electrons. Okay, these carriers are nothing but electrons. These electrons come from here, right? So this is the place where we can see all the free carriers are available. Okay, so we have given the name for this one. What is this name of this one? These electron free carriers, right? Okay, what we call it as free electrons. I can say that free electrons. What we call these free electrons? In this particular situation, inversion charge. Inversion charge. So when this inversion charge will be developed by applying the sufficient charge on top plate, right? Without applying the sufficient charge on the top plate, we are not able to, we are not able to invert the surface. Okay, that's how we got this one. So therefore, since we are applying the potential on top of the plate, therefore this is called a gate Z. Okay, this is also called as a gate. Okay. Okay, so definitely there is a this is a plate and this is also another plate. Do we see any kind of current flow from mass capacitor from top to bottom? Okay, is there any current flow here in this way, in this direction? Definitely no, no current will flow. So that means that we should say that here, whatever the current that we see here, this current is called IG, gate current, that also zero. Therefore, the MOSFET, inside of the MOSFET, the current cannot go in. Through the gate, the current cannot go. Okay, why? Because there is an insulating material between the one conducting plate to another conducting plate. Therefore, definitely the current cannot go. Right? Okay. Right. So we need to think about other two things. Okay, we have seen the N plus and N plus. So far, we have seen that. So far, we have seen that there is a free carriers that are available at this place, right? So this is also called as channel. This is also called as channel. Free carriers are available. Okay, without applying any potential difference between them. So from this end to this one, if I'm not providing any kind of potential difference, the current cannot go. Okay, why? Because once we provide the potential difference, then only the carriers can move from one higher potential to the lower potential. Carriers can move from higher potential to lower potential. Okay, so therefore, of course, definitely the carriers cannot move because we have not provided any potential difference. Okay, now let us apply the potential difference here, right? Okay, therefore, this is what the potential difference. Let us take the one terminal here. Let us take one terminal. Let us take another terminal here also. Okay, assume that let us apply here is more positive than this one. Okay, I'm so sorry. That is considered. I want to push the electrons from n this side to this side. I want to push the electrons from this side to this side. Then what potential I should apply at n plus and what potential I should apply at the right side? Left side, what potential you should apply compared to the right side? High potential where? Left side. If it is a high potential, for example, it will more potential. That means positive potential we apply here, negative potential we apply something like this. What will happen here? Since this is a positive terminal, okay, this is a positive, okay, that means all the electrons are moving this side now. And all these electrons are moving this side now. Okay. So I'm so sorry. So these are, okay, these are repelled here. Okay, these are repelled here. I'm so sorry. Let me write it this way. Okay. So therefore, these are moving in this direction. Okay, but since this is electrons, right? Okay, what I say, what I told you the carrier should move from left side to the right side. Okay, then left side, what should it be? Less. And negative that we should apply, right? Okay. Are you getting this point? Minus. Here is the plus. I want to flow the carriers from left side to the right side. Now, if I ask you to change this direction from right side to the left side, for example, then what you can say? Right side to the left side. Then what potential you should apply? Here is negative. This is positive. Are you getting the point? Okay. So if you want to send the carriers from left side to the right side, especially the electrons, we have to apply the less potential at the right side, left side, and more potential at the right side. Vice versa. Okay. Okay, since n plus both are the same, right? Okay. Suppose if you are sending the carriers from n left side to the L side, okay, if I send the carriers from, assume that sending electrons from left to right, okay, then left terminal is called source. Is called source. So the source terminal, we can call it as a source terminal. That means it's sourcing the electrons. It's sourcing the electrons to the center. Okay. And the right side and right terminal is called drain. Right terminal is called drain. Have you got the point? Okay. Suppose the same thing that I want to take it in the reverse side, reverse direction. Okay. So copy. Let me paste here. If I'm sending the electrons from right to left, for example, I want to change this one. Okay. Now I want to send from right to left. Now what this is called? What this is called? This is the left side. What is the left side we can call it as? Where it is sourcing. Sourcing from right, right? This is called then source. This is called then drain. The left it is taking all the electrons. If this point is clear to everyone? Why the terminal name is source and why the terminal name is drain? Of course, you are very familiar with now this, right? Okay. Therefore, for any reason, Okay, we can call it as this. This terminal can be a source or this can be a drain. This can be a source or this can be a drain. Okay, so therefore, whether a particular terminal is a drain or source, how do we know that one? Depending upon the potential that we are applying. Depending upon what potential that you are applying. Are you getting the point? Okay. Therefore, to say, let me write here the conclusion. Okay. To say that a particular terminal is source or drain depends on the which potential or what potential I can say. What potential we applied on the terminal compared to other terminal. Is this point is clear to everyone? Okay. So can we say that the current flowing within the channel, the moment if the carriers are moving from one direction and another direction in a given time, definitely the current will flow. Okay. So now what is the direction of the current if you take this particular option? If you choose this particular option, that means you would like to send the carriers from left side to the right side. Okay. That means carriers are moving from left side to the right side. Carriers are moving from left side to the right side. Then what is the direction of the current? So, and one more thing is that I want to write it here explicitly that it is at low potential. Okay. It is at high potential. Am I right? Similarly, here it is at low potential, and this is at high potential. Okay. We take the first case, right? The carriers are moving from left side to the electron is moving from left side to the right side. Okay. Let me take this. Assume that here, this is one point, this is another point, this is the left, this is the right. Okay. The electrons moving in this direction. Okay. This is called E. Okay. Now, what is the current direction? So the left side means left side to the right side. I'm talking about left side to the left side. What should it should be? It is the low potential we are applying. It is at a high potential that we are applying. Right. Okay. Now, what is the current direction? Current is always opposite to that of electron direction. Am I right? So therefore, and one more thing is that current is always flow from higher potential to lower potential. Right? Okay. Now we should say this is what the current flow. Agreed? Right. Now, if you take this is an option, for example, if you take this option, then what you can suggest me? That means this is the left side, this is the right side. Therefore, this is the left, this is the right. Okay, left is at high potential, right is at low potential. Now, the electrons move from right to the left, right? This is what the choice, right to the left. What is the current direction now? Current direction should be opposite. Current always flow from higher potential to lower potential. Whereas the electrons lower potential to higher potential. Okay. Okay. Good. Definitely, the current will flow from this direction, right? Therefore, whatever the current that is, for example, if I'm considering this is at low potential, this is at high potential. Okay, assume that this is at a low potential and this is at a high potential. Okay, that means the electron direction is something like this, right? And the current is actually flowing from where? From, so in this particular case, we call this is a source. This is called as a drain. Am I right? Therefore, the current is flowing from drain to source. Therefore, I ds is not equal to 0. Am I right? The current flow from drain to source is not equal to 0. Agreed? Right. So therefore, now let us consider about one terminal, the symbolic representation of a MOSFET. Okay, symbol. So symbol of N MOSFET. Okay. You know, if you want to play with NMOS transistors, for example, I cannot go and directly draw this particular structure all the time, right? For example, if 2 transistors I'm able to write, for example, 10 transistors with this particular structure, it is impossible, right? So that's the reason why I would like to create one symbol for this one to know that this is a NMOS transistor. Okay. Okay. How many terminals the NMOS transistor has got? 4 terminals, right? As you can see, there are the 4 terminals. Okay, so this is the 1 terminal. So this is how we need to write. And there is another body is also there. This is the body terminal. This is the, okay, this is what the arrow mark is always representing an NMOS. Okay, whenever you see this kind of symbol, you should say this is a NMOS transistor. Okay, so this is usually this is called the drain. Okay, of course we cannot say which one is the drain. If somebody give you the NMOS transistor, for example, then how do we decide the source and drain? First question. Okay, if somebody give you one transistor, MOSFET transistor they have given. Okay, the first question comes here is the question one, number 1. How do you know the type of transistor? Okay, we know that the 2 types of transistors, right? Type of transistors. Okay, one NMOS transistor and PMOS transistor. How do we know that whether it is NMOS transistor or PMOS transistor? Symbol they have not given. Just only they have given in the laboratory. If you go to the laboratory, you ask NMOS transistor. Some transistor, you ask some transistor. They have given a transistor. They did not mention any kind of name. And how do we know? Apply a gate potential. Okay, apply the gate potential. If you apply the gate potential is positive, if the transistor allows some kind of current, okay, then we can say it is a, of course, not only that one, we are applying the gate potential. First of all, we have to, if the gate potential is positive, it is reacting to the positive potential. Okay, if the channel is formed, then we can say that it is a NMOS transistor. Whereas the PMOS transistor is opposite. Okay, if you apply the negative potential to that one, it will on. Okay, if you apply the positive potential, it will be on for the NMOS transistor. Okay, somehow you came to know that this NMOS transistor because they have given the symbol, for example, or they said that it will be active for the positive voltages they have given. Then you should remember that yes, this is NMOS transistor. Okay, Then how do we choose which terminal is a source, which terminal is a drain? Okay. So therefore, the question number 2, how to choose type of terminals. Okay, sorry. How to choose terminals, terminal names, terminal names, whether it is a source or drain. Okay. Now tell me, how do we know? For example, if I say that apply the high potential here and low potential here. Apply the high potential there and low potential here. Now, can you say that which one, what is the source and what is the drain? What is the drain? Quickly. Upper one is a drain or lower one is a drain? What we said. So whenever you apply the highest potential, okay, that we call it as a drain for the NMOS transistor. Okay. It's a drain. Okay. It's a drain. So whenever you apply the low potential, that is called a source. That is called a source. Okay. So therefore, how to choose which potential is a source, which potential is a drain? Okay, if you're applying whatever the potential, high potential you're applying, the terminal we call it as a drain. Other terminal can be source. Or the low potential is at source, high potential at drain. Okay. Now, what is the current direction here? What is the current direction? Okay, next question number 3. What is the current direction? What is the current direction? Current is always flow from high potential to lower potential. Okay. Therefore, the current direction is something like this. Okay. Right. Let us give you one question here. Okay. Let us take the same thing here. I did not mention anything here. Okay. So whether it is NMOS or PMOS, only I have given the symbol, something like this, and the current flow direction is I given like this. Then what is this transistor? What is the source and what is the drain? I have given the symbol like this. Current direction I have given. I'm asking you what type of transistor it is, whether NMOS or PMOS. The second one is which one is the source, which one is the drain. The current I have already given. Current already given I. See, based on this arrow mark that we can say, based on this arrow mark, we say this is a NMOS transistor. That's good. And based on the current direction, the current is always flow from high potential to the low potential. That's the reason why it is called at the high potential. It is at the low potential. Okay, but the carriers are moving from source to drain, right? So therefore, the carriers are moving from lower potential to the higher potential. Since it is an electron, the carriers are moving from lower potential to higher potential. Therefore, so since it is a high, it is called a drain, and now this is called source. Or depending upon the electrons, if you want to say, okay, since low potential is at, sorry, since the electrons are moving from the low potential, that's the reason why it is called a source. Okay, so the electrons are drained at the high potential, that's the reason why it is called drain. Okay, two ways that we can say. Either the potential point of view you can say, or otherwise by the electron direction that you can say whether it is a source or drain. Okay, so two ways. What are the two ways? What are the two ways? With the help of potential with the help of potential or with electrons. Okay, the direction of the electrons I can say. Okay, yeah. This is how we have to say whether it is an NMOS transistor or PMOS transistor. Okay, by the arrow mark we can say it's an NMOS or PMOS. By the direction of the current, we can say whether which one is the source or drain, or by the electron direction also we can say whether it is this one. Hopefully you catch this point, right? So this is very important. So the current direction, okay, finding the source and drain of a MOS transistor is very important when we are analyzing the analog circuits, right? Okay, so if I say that what is the current direction of that particular, and in a particular circuit, analog circuit, if I ask you, you should be in a position how the what are the potentials at the particular nodes, and depending upon the node potentials, we should say the current direction is so and so for NMOS as well as the PMOS. Okay, that is the reason why we discussed about this. Similarly, we take a PMOS transistor. Okay, let's talk about the physical structure of PMOS transistor. Okay, so what modification that you can do on this particular one? By the way, I want to give you one simple conclusion here also again. Okay, so you know what is IB? IB stands for the current through the gate. The current through the gate is zero. Sorry, IB stands for the body. Okay, and what is the IC here? IC is also zero. Current through the gate is zero, but the current through the source terminal and the current through the drain terminal both in the same. Okay, whatever the current into the source from the source, and the same current will also see at the drain also. That means whatever the current that is flowing from here, the same current is also flowing from here also, right? This is called the drain terminal. I'm so This is the drain terminal and source terminal. Okay, if this point is clear, drain to source, the current is the same, right? Or I can also say that the IDS is source to drain is usually may not be zero, or make zero, or may not be zero. That's depending upon the potential. Okay, I don't want to conclude at this point of time. Okay, let it keep it like that. Okay, whatever the source current is, the drain current is the same. Right. Let's take the PMOS transistor again. Okay, take this PMOS transistor. OP.
Can you suggest me what are the relevant things that are required for this PMOS transistor? See? What are the things that I should remove and exchange? What are the things that I need to remove and change the quantities? What should be this one? This should be N substrate. Okay. What is the body here? Body is actually N plus. Okay. Body is N plus. What is the source terminal and drain terminal? What is the source terminal and drain terminal? P plus and P plus. Right? Okay. What are the immobile carriers type? It should be positive, right? Okay. So what is the potential I should apply at the on the top plate? What should I apply at the top plate? If you want to deplete the electrons, we are now going to deplete the electrons. Therefore, here, this is the plus over, this is, we can write it as something like this. This is called atom. Okay. This, when we remove this particular electron, for example, then definitely it become an ion. Therefore, the ions I have shown there. And what are the carriers that we have here? Okay, if the capacitance is less, then equal and opposite charge must be provided behind the or below the silicon dioxide. That's the reason why all holes are contributed to form a channel, right? Holes are contributed below the channel. These are the free carriers that are available here. Am I right? These are all free carriers. What is the type of the free carriers? Holes. Okay, now come to the point. For example, if you want to, again, this is also holds good, right? This is also holds good. This is also holds good, no doubt. Okay, and one more thing. What is the potential that it should apply for the body? Can anyone help me? You want to make it reverse bias, right? Okay, if you want to make the reverse bias, what should be the potential at the body? Okay, what is the PN junction diode that is formed here? It is something like this, right? This is N plus and P is the body, right? So something like this. So what is the potential I should apply here? Okay, so that this particular one is always in the reverse bias, irrespective of whatever you apply here. Or otherwise, I want to reverse this one. Okay, okay. If you are confusing, for example, I will take something like this. This is the P, this is the N plus. Okay. So now, what is the potential I should apply here, irrespective of whatever it applied, it becomes a reverse bias. Higher potential, right? Very good. So if it is higher potential, for example, 5 volts that I'm applying here, 5 volts. Okay. If it is 0, what happened to this one? 0 minus 5, minus 5. 1 I'm applying here. 1 minus 5, minus 5. Okay. Something like this, 5 minus 5, 0. 6 minus 5, 1. That means, as you can see, if you apply the positive potential at the left side, okay, so therefore the value, whatever the value that you observe here, okay, to make the, actually, what potential applied we need to apply here is the reverse bias, means here we have to apply more potential, or I can say the more strength than this one, less strength. Okay, less strength means that if you're applying 1 to positive values, if you give, it cannot be a less values, right? Less values means that from 0 to minus values. If you want to make it very strong reverse bias, then what we have to do? We have to apply more negative on the left hand side. Therefore, instead of saying this one is in the upward increasing fashion, 0, -1, -2, -3, so on and so forth, we have to increase, we have to give. These are called less values, right? Therefore, this is absolutely, now this is absolutely becomes reverse bias. That's the reason why you always remember that we have to apply the highest potential. Normally, we can call it as drain potential is the supply voltage we normally give. Okay, highest potential we have to give to the body of PMOS transistor. Is this point is clear? Right. Okay, and that is the one point. The second point is, for example, if you want to move the carriers from the left side to the right side, in this particular case, what potential I should apply at this place? What potential I should apply at this place? Is it high potential or low potential? Yeah, tell me. What potential I should apply at the left side if you want to move the carriage from left side to the right side? High potential or low potential? High potential. If you apply a positive potential there, then the positive potential repels the holes towards the right hand side, right? If you apply a positive potential here, then holes can move this side and it will enter at this side. Okay, now here, this side actually sourcing the holes, right? And this side capturing that or draining or sinking that holes, right? So therefore, this is called a source at this point of time. Am I right? Okay. And this is called the drain. Okay. What about if the carriage want to move from right to left then? Right to left. That means now we have to apply more potential here and less potential at this place, right? Now, according to this particular scenario, what is the source here now? The source is here, the drain is here. Okay, that's the reason why either this is can be a source or drain. The right side the element, the material can be acting as source or drain. Left side can be acting as a drain or source. Okay, therefore we cannot say directly unless otherwise what potential that we are applying at the drain and the two regions. Are you getting the point? Okay. Now, okay, this kind of explanation just you have to go here. Here is the three holes that we have, right? The holes contribution we have to talk about. Here the inversion charge is actually the holes, okay? And the channel is nothing but the holes. Okay, now we can, so these things are self-explanatory, then you can go through it, okay? But now I want to tell you this particular symbol point of view, let me discuss about it. Let us discuss about the symbol point of view. Okay. It takes a lot. Okay, look at this. Okay, right. Look at this. Okay. Okay. So this arrow mark represents a PMOS transistor, right? This arrow mark represents PMOS transistor. Okay. Now let us assume here I'm applying the high potential, and here I'm applying the low potential. Okay. Now where the current will flow? What is the current direction? In case of electrons, okay, in case of electrons, where the electrons, if it is low, for example, it is high, the electrons flow from, if it is electrons, it is flow from left to right. Okay. Whereas in the form of holes, for example, if it is holes, for example, those are, okay, because of this one, the current will flow from in the opposite direction. Okay. Now what about this carriers here now? These are coming from this direction. Holes are come from always high potential to the low potential. Okay. Now what about the current? Current always flow from high potential to low potential. That means it always follows the whole direction. It always follows the whole direction. Okay, right. Okay, so now what is the carrier transportation here from low to high or high to low? Carrier transportation from high to low. In the same direction, this is the whole direction, and the same direction also, the current is also flowing. Okay, definitely the high potential. What is the high potential we can call it as? Can anyone help me? What is the low potential we can call it as? What is the high potential terminal we call? It's a it's a source, right? It is a source. Be careful while you are talking, right? It is a source. Okay. What about that low potential? Electrons. Sorry, this is called drain. This is the drain. Okay. For example, if I ask you, the current direction is, the current direction is opposite, for example. Just I say that the current direction is opposite. I've given something like this. Okay, not this one. I'm not giving in this one, but I'm giving in this way. Okay. Then can you please tell me what would be the source? What would be the drain? PMOS I have given, current direction I have given, and I'm asking you what is the source, what is the drain? Which quantity you have to think about. I'm not mentioning about which one is a low potential, which one is high potential. I did not say anything about it. Okay. I have just shown the current direction from bottom to top I have given. What immediately think in your mind should be thought in your mind? The current always flow from higher potential to lower potential. Then immediately you have to pick that this is the low potential. Sorry, it is at a high potential, and this is at a low potential. So because of this one, you should say, since it is a PMOS transistor, high potential is at a source, low potential is at a drain. Is this point is clear to everyone? Okay. So for this is how we have to identify whether it is NMOS transistor or whether it is a PMOS transistor. That is the first thing. The second thing is that based on the direction of the current, for example, only they have given the direction of the current, then you have to properly choose which one is a source or which one is a drain. If they have given the potentials actually, then you should know how the current will flow. Okay. So all these things are very, very essential when we are discussing about the analog circuit. Okay. So we stop here at this moment. Okay. We'll take some time and we'll come back.